Thank you very much. That's not the first time I participate to this conference. Usually the weather is a little better than today. It's raining here in Marseille. What I'm going to talk about is the Boussinesq system. And the idea came when I was at the PhD defense of Jiaohe, a student of Lorenzo Brandolese. So the Boussinesq system so uniqueness in critical spaces and of course, if you know me, it's using maximal regularity. So the whole thing is about, so as I must say, it's a joint work with Lorenzo. Okay, so the system can be written this way. So it's dtu minus Laplace nu plus grad the pressure term, and now there's the nonlinearity. So how is it? Yeah, it's this way. It's theta E3, so we have E1, E2, E3. We are in the whole space R3. We have the incompressibility condition, the divergence of U is 0. And theta is the temperature. It's coupled with the velocity with a transport term. So it's dt theta minus Laplacian theta plus u dot grad theta equals 0. So this is, the whole thing is in 0t cross R3, right? So u of tx is a vector field, and theta is a temperature, so it's real. And the problem is, so what are the critical spaces for this equation? So if you just forget about the temperature for the Navier-Stokes, incompressible Navier-Stokes equation, what you would need is, what you would want is the velocity continuous in time with values in L3. Okay, so that's what you are looking for. And also with the everything for the temperature, if you look at the scaling properties of the equation, what you would have is theta continuous in time with values in L1. So the first problem with this is that even if you write this as the divergence of theta u, you see that if u is in L3 and theta in L1, it doesn't work well, right? So that's why, so to multiply something like that, the best you would expect for is a is a theta in L3 half. So the invariant, the critical space, if you take the temperature with values in L3 half, would be in time L2. Okay, I don't want to do the whole calculations, but believe me, it works that way. So that's the critical space. What Jiahoe did was having something a little less in time, so something a little less than L2, but a little more than L3 half here. And it works easier if you have something. The problem here, there's another problem now, is if you multiply theta with u, then you end up with something in L1, and everybody knows that L1 is not a good space. Well, it doesn't work well anyways. So how to achieve that? So yeah, I didn't write down the initial conditions. So u at 0 is a u0, and theta at 0 is a theta 0. Of course, if theta, so u0 is in L3, divergence free. If you take theta 0 in L1, you are not in here, right? So you have to be in the correct Bezoff space to have at least, well, a solution without the nonlinear term to be in this space. And the correct space, well, hope I'm not mistaken, it will be b minus 1, 3/2, 2, or 2, 3/2. I hope that's this one. So it's something which is strictly included in L1. Okay, but we won't talk about existence here. So assume you have a solution u theta of this system in this space, and what you would like to know is whether it's unique, right? So the uniqueness reads this way. So how do I? So u of t can be written this way. So it will be e t delta u0 plus or yeah, there's a minus maybe, integral from 0 to t e to the t minus s delta, the projector, so this is the Loret projector, of theta, gradient of u of s cross u of s ds, and plus this integral from 0 to t e to the t minus s delta, the projection applied to theta s e3 ds. Okay, so that's and this thing I write like a plus b u plus l of theta. Okay, so the BUU is this one. This is quadratic in U. And L is linear in theta. And theta of t can be written as e to the t delta theta 0 plus the nonlinearity, which is integral from 0 to t e to the t minus s delta divergence of theta s u of s ds, and this one I write like b plus c of theta u. Okay, so this is nonlinear, a product of theta and u. Okay, so that's just to make the notations more or less clear for everybody. So a C is clear. Maybe the B, I should write it, B of uv of t is minus integral from 0 to t, the convolution with the heat semigroup times p gradient of u of s cross v of s ds, all right? It's just as a definition. So what is the uniqueness? So how can we, so a solution u theta for us is a mild solution, so it's a couple which satisfy these two equations, right? So solution of the Boussinesq system is u theta in C0t L3. I won't write down R3 to the power 3 every time, right? Because it's a little long. C0t L1 for the temperature, and also L2 0t L3 half. Okay? And this is a solution satisfying u equals a plus b u plus L theta, and theta equals b plus c theta u, right? So there's no PDEs anymore here. So this is what I would like to call a solution, a mild solution for the Boussinesq system. So assume that there are two solutions, u1, u2. So u1 theta 1 and u2 theta 2 are two solutions. So if you write u to be the difference, u1 minus u2, and theta to be theta 1 minus theta 2, it's easy to see that u satisfies bu u1 plus b u2 u plus L of theta. So L is linear, so L theta 1 minus L theta 2 is L theta. And theta satisfies C of, so let's see, theta u1 plus C of theta 2 u. I hope I'm not mistaken, but I think it's exactly that. Okay, so the idea is to, well, if you remember what happens for when theta is 0, just for the incompressible Navier-Stokes equations, you have everything. You only have this equation here. And the way we can prove uniqueness is using maximal regularity for the heat the heat semigroup. So what is this? So assume that you have, so how can I, so there exists so for all PQ between 1 and infinity, there exists a constant CPQ, such that for all f in LP 0t with values in LQ R3 delta RF LP LQ plus DT RF LP LQ is bounded by the CPQ F in LP LQ, and I write down exactly what is R. RF of T is the convolution between the heat semigroup and F. Okay, so you see, if you put a delta in front of this is kind of a singular integral, because the delta e to the t minus s delta behaves like 1 over t minus s, right? So it's not integrable in t. Actually, what you can prove as well is you can have any dt alpha delta minus delta to the power 1 minus alpha rf as well. So any mixed derivatives here for all, so this is also for all alpha between 0 and 1. Okay? So that's the way I will use maximal regularity. What is RF? So if you write U equals RF, U satisfies dTu minus Laplace mu equals F, U at 0 is 0, right? So it's formally, at least, it works like that. Okay. And now I'll use that to prove some results on my operators B, C, and L. So maybe I write down exactly what happens. It's a little technical to prove everything, but the first proposition is for all epsilon, for all V and W continuous in time with values in R3. There exist. Oh, I should have said here, I can take t equals plus infinity, and the CPQ is independent of t, right? So CPQ is independent from t. Okay, so you can have the same constants for any t. So this is allowed, right? So t is positive, but less than or equal to plus infinity. So yeah, so, no question. Sorry. There exists a tau. So tau depends on epsilon v and w. Such that, so if I write b, so I look at the operator b with respect to the first variable as a linear operator, but plus bw dot. So this goes from L4 0 tau with values in L6 into itself. Is bounded with norm less than or equal to epsilon. Okay, so if you make the interval smaller, you can have a norm as small as you want. Okay, so that's the first result. It's really just using maximal regularity to prove that. The second proposition is about the operator C. It works, so it starts the same for all epsilon positive, for all V continuous in time with values in L3. There exists a tau, which is a tau of epsilon and V, such that, so you see the C, where is it? Here. C can be, so there are two parts in the C. So this one is more or less the good one, but that one is maybe where the nonlinearity comes from. Right. So such that the C dot V, this goes from L, no, so it's 4/3, 0 tau L2 into itself. This is bounded with norm less than epsilon. So, sorry. Can you read it? Maybe. How can I do? Too high. So that's the first part. And the second part is, maybe I should write it down here. For all epsilon positive, for all theta in L2 0 tau3/2, there exists a tau. Of course, I always call them tau. They are different, but then we take the minimum, right? So this tau is a tau of epsilon and theta. Such that so this C theta dot. So here comes the U, right? So U, the right space would be L4, L6 into L4 third 0 tau. L2 is bounded with norm less than epsilon. Okay. So again, it's using the maximal regularity property, maybe in a clever way, but it can be done. And now the last one would be L. What happens with the operator L? I don't want to make a mistake. So the last proposition is for all tau L maps L2 0 tau L3/2 into L4 0 tau L6. So with norm independent of tau. And it maps as well L 4/3 0 tau L2. Okay, yeah, sorry. Can you see now what happens? Into the same space, L4, 0 tau, L6. Also with norm, less than, independent from tau. So in the last proposition, I don't have anything with an epsilon, right? I don't need the norm of L of theta to be small. And actually, I cannot do it. But all right. So once we have these properties, we are just in the position to state and prove the theorem, well, a theorem about uniqueness. So the theorem is the following. Well, actually, there is only one. So if there is maximal one solution. At most one solution there is. U theta, so continuous in time with values in L3 and theta in L, which L2, L3 half. Of the system, U equals A plus B, U plus L theta, and theta equals B plus C theta U for A So if I write this to be xt, this is for AB in the space xt. Okay. So now how to prove that? I don't know whether I have much time to do all the details, for sure not, but let's maybe but now, okay, let's see if I can do it a little better. And okay, let's see. Well, the propositions are not visible, but well, maybe you remember how they look like. So maybe about the proof. So remember, so U is B U U1 plus B U2 U plus L theta. What we know is that U1 and U2 are continuous in time with values in L3, and theta 1, theta 2 are L2 with values in L3 half, right? So what our proposition 3 says is that, so theta 1, theta 2 are in here, so theta 1 minus theta 2 as well, right? So it says that this one is in L4, L6. So that's the second, do you see it? It's the second part the second part, first part of proposition 3, right? So this is Je sais plus. Là. Okay. So what we know as well is that that one, for all U1 and U2, the norm of that in L4, L6, so 0 tau, is bounded by epsilon times the norm of U in L4, L6, right? So it means that the identity minus this as a linear operator is invertible, and we have that the norm of U in L4 0 tau L6, so 1 minus epsilon is bounded by L theta in L4 L6, right? So I'm not saying that U1 and U2 are in L4 and L6, but the difference is, well, actually the difference we want to show that it's 0, so it better be in L4 L6, right? So this is in a small interval. Okay? And so we can take epsilon equals a half, right? A half is good. And for the second part, the fact that theta is C of theta U1 plus C of U2 theta. So what we showed is that one, well, actually there are two parts. So the first part, the norm of that, so it comes from proposition 2. For the first one, it's the proposition 2 second part, is that one in L 4/3 0 tau L2 is bounded by epsilon times theta in the same space, L 4/3 0 tau L2, right? So the tau depends on U1. U1 is given, right? It's we assume it's a solution. The same as here. This tau here depends on U1 and U2. So that was only for the first part. Here. And for the second part here, what we know is that, so this is the proposition 2, the first part of proposition 2. I'm afraid we cannot see it anymore. Just have a look. Yep. So it says that no, sorry. This is a theta 2 U. So for this part here, I use the first part of proposition 2, which says that this one in norm L 4/3 0 tau with values in L2 is bounded by epsilon times U in L4, L6. Right? No, sorry. So that's the other way around. That's this proposition 2, 2. And that's the proposition 2, 1. And this tau depends on epsilon and also of theta 2 in L2 of L3 half, where my solutions are. Okay. So now we are almost done. And I will hurry a bit not to miss the coffee break. Now we have everything, because now we have theta, so there's a 1 minus epsilon theta in L 4/3 0 tau L2. This is bounded by U in L4 0 tau L6. So we just now use the two estimates, plus the fact that L is bounded from L 4/3 with values in L2 into L4 with values in L6. So L4 0 tau L6 is bounded by a constant times theta in L4/3 0 tau L2, right? So putting everything, so that's the proposition 3, the second part. So I used proposition 3 twice. First, to show that L theta is in L4, L6, and here to have the estimate with the right space, the space I want. Right? So if we put everything together, I think we are good. So taking epsilon small enough, how is it? I'm lost. I think we have everything we need, right? So we have 1 minus epsilon u. So L4, L6 is bounded by a constant times theta in L4 third L2 let's see, I think is there something missing? And now that one, oh, C 1 minus epsilon u L4 L6. No, there's something wrong here. There should be an epsilon somewhere. Let's see. Yeah, there's something, I forgot that the theta here is not, no, that's, there's an epsilon here. Oof. So, what is it? Theta, here I still have an epsilon. So making epsilon small enough, we are good. So u is 0 on a small interval, then theta is also 0 on a small interval, and then we conclude as usual for uniqueness. So thank you, and that's all for my talk. Yeah, I see you. It's just a big advertisement for maximal regularity.
I have a quick question. So this is Patrick.
Yeah. Hi, Patrick.
From Germany. What about the existing part, actually?
Well, we hope to prove it as well. It should be the same. If you take a theta, an initial condition for the temperature in the right Bezoff space, this should be well, not easy, but feasible. I'm confident with that. Also, using maximal regularity, we have everything we need. So we didn't have time to do it, but maybe we will have some time this week.
Thank you.
There would be another question, Matthias.
Yes. Yeah. Okay. Hi, Matthias.
Are the spaces you are considering, are they scalably invariant?
Yes. So yeah. So the L4, L6 is a scale invariant for the velocity in the Navier-Stokes equations, and you see the L4 third of L2 is also critical for the Boussinesq equation. So if you just look at the temperature equation, yeah.
Okay, thank you.
Delta, do you have a question?
Hello everyone, how are you?
I'm good, thanks.
I have a small question because at the beginning the presentation regularity was L2, 3/2 for the temperature.
Yes.
So my question is, if it is possible to relax this L2 in time.
To have something less than L2 then?
Yeah.
I'm not sure. We are always on the edge here. It's also it's always critical. So we are just having the right properties using maximal regularity. So I'm not sure I can relax this L2. it was already a big step to go down to L3½ in space.
Okay.
And I'm even not sure it's true. What would you like? Something like L1 or L?
No, it's not a question what I like, but what are the possibilities?
As far as I know, L2 is the critical space. L2, L3½. I cannot do anything better.
Okay, thanks.
Okay, so are there further questions or remarks?
Is there something that's missing about the continuity in time of the temperature? Sorry.
In the statement of the theorem, isn't something missing about the continuity in time of the temperature? Because you use the argument that, first of all, you prove the uniqueness in a small time interval.
Yes.
But then if you want to have the uniqueness in the whole interval 0t.
Yeah, that's true. So maybe my space xt should contain as well continuous in time with values in L1.
Continuity in time to grant the,
yes.
the uniqueness in the whole time interval.
Yeah, I think so. Well, I didn't have enough space to write it.
Yeah.
But you're right. I didn't work it that down the whole. So maybe it works in L2 only, but I'm not sure.